Hi, we're Team 8 we're going to discuss about the photovoltaic system. My name is Sarah Kane.
I'm Mauricio Martinez.
And I'm Suraj Alini.
I'm going to explain about how photovoltaic system, PV system in short, it works. The Earth intercepts the solar energy approximately 173,000 terawatts, which is 10,000 times more power than the planet population uses. Because of the abundant resource we can use from solar energy, it is credential to understand photovoltaic system, which is PV system is short. A PV system is a system composed of one or more solar panels combined with an inverter and other electrical and mechanical hardware that use energy from sun to generate electricity. First, I'll explain how the solar panels convert energy to electrical energy. The solar panels are made of smaller units called solar cells. The most common solar cells are made from silicon, a semiconductor that is the second most abundant element on Earth. In a solar cell, crystalline silicon is sandwiched between conductive layers. Each silicon atom is connected to its neighbor by four strong bonds, which keeps the electron in place so no current can flow. A silicon solar cell uses two different layers of silicon. An N-type silicon has extra electrons, and P-type silicon has extra space for electrons, called holes. Where the two types of silicon meet, electron can wander across p-n junction, leaving a positive charge on one side and creating negative charge on the other. You can think of light as the flow of tiny particles called photons shooting out from the sun. When one of those photons strikes the silicon cell with enough energy, it can knock an electron from its bone, leaving a hole. The negatively charged electron and location of positively charged hole are not free to move around, but because of the electric field at the p-n junction, they'll only go one way. The electron is drawn to the N side while the hole is drawn to the P side. The mobile electrons are collected by thin metal fingers at the top of the cell. From there, they flow through an external circuit, doing an electrical work before returning through the conductive aluminum sheet on the back. Each silicon cell only puts out a half a volt. So as you can see in the right picture, uh, we can string them together in modules to get more power. 12 PV cells are enough to charge a cell phone, while it takes many modules to power an entire house. Electrons are the only moving parts in the solar cell, and they all go back when they came from. So the solar panels can last a decade.
So I'm going to talk about the application of PV systems. We have different types of solar PV systems. We have the grid-connected PV systems, off-grid PV systems, hybrid PV systems, and PV-based systems. These systems can be used for different reasons. Like the grid-connected PV system can be used for large-scale productions and can be used with or without battery. The off-grid PV systems can be used with or without batteries as well in houses and industries and for like PV water pumps. The PV-based utilities can be used in solar lamps, and the hybrid PV systems can be used in diesel hybrid and wind PV hybrid systems. We're going to go much deeper into specific PV systems. And on the next slide, I will be talking about the PV systems in the residential homes. As you can see, the sun is providing solar energy to the panels, and the panels, the PV cells, turn this light into DC electricity. And in DC electricity, the current flows into the inverter, which converts it to AC electricity. And the current feeds through the meter and then into the home appliances and units. Free electricity is generated when active, and the ones that are not being used, the energy that's not being used, goes back into the grid for others to use. This is a typical example of a grid-tied PV system. On the next slide, here's a little case study of Eppright Hall here at Texas A&M campus. This shows two different setups of a PV system. The one on the first shows more panels, while on the one on the right, the second setup shows less panels. As you can see, due to the number of panels, you can tell the output that it would offset. And here on the left, it's going to offset about 90% of energy, while on the left, less than 10%. This also tells how expensive it will be, the system size, and the expected payback time. So when you're about to purchase a good PV system, here are some criteria and that you should consider when purchasing or installing a PV system. The system output, the payback, the panel numbers, and the system size. So this in total summarizes um, my slide.
All right, so I'm going to be going over some difficulties and or challenges associated with the PV systems. So in general, the performance of a solar cell is measured in terms of its efficiency. And looking at the measures from a typical commercial solar cell in 2019, it had an efficiency of about 19 to 22%. This means that about 1/5 of the sunlight that was hitting the cells actually generates electricity. And this can create some problems because it's also weather dependent. This means that location plays a huge factor in where you're going to get this electricity from, because the solar radiation can be very dependent where you're located. Some places such as the Southwest are significantly more solar radiation than other locations such as the Northeast. So it's just very variabilistic. It's not very consistent. But there is some progress going on with the cells these days, because if you take a look back to the first solar cells that were made in the 1950s, they only had an efficiency of about 4%. So if we can keep getting this efficiency to rise, we can start reducing the cost, which I'll talk about in the next slide. And so these setups aren't affordable for everyone still to this day. So if we're looking at a national average in the United States, an 8 kilowatt capacity setup would range you about $15,000. But this is still a pretty good decline from where it was in 2010, because in 2010, the national US average for the same kind of setup, but only 6 kilowatt capacity, was about $50,000. So there is a good decrease, but really that's not still affordable to everyone. We're still going to have to make these more efficient so that these costs are lowered and we can have a lot more people using this kind of setup. And so, like I said, again, it's just very variable dependent, such as the region, the electricity cost, the energy use. And once we can control the way that we make these arrays, we can actually start making them affordable to everyone. And this is our works cited, and thank you for listening to our presentation.